All right, so we took a look at the instantaneous power for systems that are undergoing sinusoidal steady state, and we came up with a relatively large equation, which was the sum of three terms. We also defined real power, we also talked about reactive power, and we took a look at the power for a purely resistive load. We now want to switch gears slightly and take a look at the power for purely inductive circuits. So this is the power for purely inductive circuits. And we want to be able to go back to those instantaneous power equations and make a few observations regarding this. The first thing that we really want to take a look at is when it comes to a purely inductive circuit, how are the voltage and the current related to one another in terms of their phase shifts? And we're actually going to make a general observation about this. So suppose that you had a circuit that was purely inductive, an inductance L, and we place a voltage across this, and there's a current I that happens to be 1. We know that the IV characteristics, the analog to Ohm's law for resistor, is in differential form is such that the voltage is equal to the inductance times the time rate of change of the current. But we also know the mathematical form for both the voltage and the current. So the voltage itself, since it is sinusoidal, must have the form Vn times the cosine of omega t plus theta sub v, and the current has the same form like this. Notice that we can actually plug these back into that equation, take the first derivative, and when we actually do that, so let's actually use these in there. On the left-hand side, we're left with Vm times cosine of omega t plus theta sub v. And on the opposite side, we have L times the time derivative of I sub m cosine omega t plus theta sub I. The time derivative is only going to touch this part, and the time derivative of a cosine is minus sine. So in carrying out that operation, I end up with minus omega times L times I sub m times the sine of omega t plus theta sub I. Now, to be able to see what the relationship is between the phase constants for the voltage and the current, I have to kind of mathematically massage this equation a little bit to make it look like a cosine. And I'm going to call upon a trig identity. The trig identity is that minus sine of any angle whatsoever is equal to the cosine of the same angle plus 90 degrees like this. Notice that I can essentially absorb this minus sine and this sinusoid using that identity, and I can rewrite that side in the following manner. So the left side is left untouched, but by using this identity, I can turn that sinusoid into cosine of omega t plus 90 degrees plus theta sub I. Now, in the sinusoid, inside the argument, those two are the same thing. And because this is a cosine on each side, it must be the case that this is absolutely equal to that. So these two are equal. And that's an important property. The property for capacitors is such that the voltage phase constant must be equal to the current phase constant plus 90 degrees. This property for inductors can also be verbally stated as by saying that in an inductor, the current lags, this is an important term, the voltage. So this is an important relationship. On top of that, based on the relationship that we just derived based on the IV characteristics, notice that the term theta v minus theta I, coming directly from that top equation, must be equal to 90 degrees, right? I'm going to box this one not in red, I'm going to box it in green because I'm going to use it here in a second. Going back to the power, so the power itself, this was the instantaneous, was P plus P times the cosine of 2 omega t minus Q times the sine of 2 omega t, where P itself was V sub m times I sub m. And this is the crucial part times the cosine of theta v minus I, and Q was V sub m I sub m over 2 times the sine of theta v minus theta I. Now notice, right, if this happens to be a capacitive load, then that right there is 90 degrees, that right there is 90 degrees. And the cosine of 90 degrees very beautifully is 0. So this is 0 for a purely inductive load. Or inductive circuit. While the sine of this very happily is, I put I, it's not I, it's 1. Like this. Right? So the instantaneous power itself for a purely inductive load is minus Q times the sine of 2 omega t. Now notice that this right here is constant. There's no real power that's actually being delivered, right? Even over one period, you can actually take the average of this, and essentially it would boil down to taking the time average of a sinusoid over its period. Notice that this itself happens to go to 0 altogether. And this is one of the reasons why we say that inductors themselves can deliver a certain amount of power and store it, or it can actually deliver a certain amount of power, but it can never generate its own power. And that's a really extremely important property of inductors, right? They can never generate power. They can store a certain amount of power and then release it back into the circuit at a later time. But they can't actually do any real work on the circuit. And in the next one, we'll take a look at purely capacitive loads.